Bismillah ar-Rahman ar-Rahim. Now we are going to continue our explanations of dynamics, integration of vector function. Okay, as we said during explanation of differentiation of vector function, we have three vector function relating to the motion of a body in a straight line. Okay, here we have displacement function S function, and we can express this displacement in algebraic measure S. We have velocity, okay, function V, we can express it at V, and we have acceleration, okay, acceleration A, and the algebraic measure of this vector is A. Okay, and we explained how to drive each of these vector function from the other. Okay, here we have integration is the anti-process of differentiation. If we have f of x by differentiation here, okay, we will find f dash of x. Okay, and in opposite way, if we have f dash of x by integration, we can find f of x. Okay, here we have, for integration, we have two types of integration. We have indefinite integration and we have definite integration. Okay, the symbol of this one is like this, and we have here the same symbol, but we have here lower limit a and upper limit b. Okay, here we can use this two types of integration to find each one of these vector function by using the other vector function. Okay, first we study how to find velocity. Okay, velocity by using this integration, two types of integration. Okay, as we said during explanation of the differentiation, we have acceleration equals dv dt. Okay, then by separate the variables, okay, we can find dv and take the integral, indefinite integral. Okay, then we have indefinite integral of dv equals integral of a dt. Okay, then by doing the integration, we have velocity here equals integral a dt, and this is equation or relation number one we can use to find v from a by using indefinite integration. Okay, also we have, if we use definite integration, okay, then we have here integral from v naught to v, okay, dv from this equation equals here we have t0 to t a dv, and from this one by doing integration we have v minus v naught equals the definite integral from t0 to t a dv, and this is second equation by using indefinite using definite integration. Okay, in case of acceleration is constant, okay, if it's mentioned in the problem, or during the movement or motion of a body under the action of the gravitational acceleration, okay, then a is constant in these cases, and we can use this relation v equals v naught plus at, okay, to find the velocity of this body from the acceleration in case of acceleration is constant, and this is rule or relation number 3 we can use. Secondly, we can find displacement vector. Okay, S, algebraic measure of displacement vector S, okay, from velocity, okay, by using integration. Okay, here we have v equals ds dt. Okay, by separate the variables, then we have ds equals, and take this integration here we have indefinite integration of ds equals indefinite integration of v dt. Okay, then we have s equals integral of v dt, and this is question number 1 by using indefinite integration. Okay, here if we use definite integration, we can put here the limits, lower and upper limit. Then we have here s0 or x0 and s ds, okay, equals integral from t0 to t v dt. Okay, by executing the integration, then we have s minus s0 equals integral from t0 to t, okay, v dt, and this is second relation. We can find displacement from integration of velocity, okay, by using definite integration. Okay, when acceleration is constant, we can use this formula, s equals s node plus v node t plus 1 over 2 a t square. Okay, by executing this definite integration, we'll find this one if acceleration is constant. Okay, then this third relation from which we can find displacement from velocity and in case of acceleration is constant. Okay, and finally we have this relation a equals v dv ds when v velocity is a function of displacement x or s. Okay, then by doing by doing the variable separation, here we can find integral of v dv equals integral a ds. Okay, then this is first relation. Also we can find we can use to find v if we have acceleration. Okay, also by using indefinite integral. If we use definite integrals, then we have here integration from v node to v dv equals integral from s0 to s ads. By executing this definite integration, then we have half v square minus v node square equals integral from s0 to s ads. Okay, and this is the second relation we can use also. Okay, in case of acceleration is constant, a is constant, then we can use by applying the integration or executing the integration of this second relation, we can find v squared equals v naught square plus 2as, and this is third equation we can use to find velocity if we have acceleration. Now we can summarize what I have explained before. We have three ways to find vector function, okay, functions relating to the motion of a body in a straight line using number one, indefinite integration, okay, and number two, using definite integration, number three, when acceleration is constant. Okay, first for velocity, okay, v, we can use this relation v equals indefinite integral of a dt, okay, or we have v minus v node equals integral from t0 to t a dt by using definite integration. Okay, and in case of acceleration is constant, then we have v equals v node plus at. Okay, this is the three rules or relation we can find v, okay, by using indefinite integration, definite integration, and in case of acceleration is constant. Okay, for this relation here, if we have this relation between acceleration and time, okay, here we have this curve representing this relation between acceleration and time of a body moving in a straight line. Okay, here we have between t node to t1, for example. Okay, the area under this curve equals v minus v node. Okay, then this area equals V minus V node, as the area can be expressed as integral from T node to T a dt. Okay, then this area under this curve representing the relation between acceleration and time equals V minus V node. Okay, now we can move and explain how to find displacement. Okay, yes, by using the same three rules. Then we have x s, for example, or x displacement equals indefinite integral of v dt, this first relation, and we have s minus s naught equals integral from t naught to t of v dt when we are using a definite integration. If acceleration is constant, then we have s equals s naught plus v naught t plus half a t square. Okay, this is third relation. For this one also, if we have a relation here between v and time t, then the area under this curve vt during t naught to t1, for example, this area equals s minus s naught according to this relation, as the area under this curve vt during t naught to t1 can be represented by integration from t naught t1 v dt. Okay, and finally, if we have this relation integral of v dv equals integral a dx when v is a function of displacement. For s, for example, s or x is the same. Okay, here by doing the definite integration, okay, then we have half v square minus v naught square equals okay, integral from s0 to s a ds. Okay, in case of acceleration is constant, we have v squared equals v naught square plus 2 a s. Okay, we can use this relation. For this one, if we have this relation between acceleration and s displacement, then we have this relation or this curve representing this relation between a and s at s equals 0 to s equals s1. For example, here the area under this curve represented the quantity half v square minus v naught square according to this second definite integration relation. Finally, we have to differentiate between displacement s and distance x. Okay, displacement here we can find displacement, for example, from this curve relating the relation or expressing the relation between velocity and the time of a motion of a body moving in a straight line. You have here s minus s naught equals integral from t naught to t v dt. Okay, and this quantity is the area under the curve vt, okay, during 2 t naught to time t. Okay, as displacement is a vector, then s can be positive or negative. Okay, then to find the displacement from t1 to t4, we have here s equals area, this area 1, and this have its positive quantity here as it's above x-axis. Okay, and we have minus a2 here, the area of this triangle. Okay, and this is in having a negative sign as it's drawn under the x-axis representing the time here. Then finally we have to add area A3. Okay, by adding these three quantities with using the correct signs, then we can find the displacement of the body from T1 to T4 using VT curve. Okay, here we can find also displacement x from t1 to t4. Okay, as displacement is always positive, okay, we can use s minus s naught equals integral t naught t v dt, but we have used modulus in this case, okay, as distance here is always positive, okay, then we have to use modulus in this relation as in this form, okay. Then by applying this rule in this curve, you can find the the distance moved by a body moving in a straight line from t1 to t4 according to this 2vt relation. Then we have here s, we can express it at x here equals as distance equals a1's area under the curve during the time interval t1 to t2, and here in positive as we use modulus, okay, here plus a2, okay, this area but in positive sign from t2 to t3, and adding a3 also the area of this triangle from t3 to t4 by positive sign as well. Then x is always positive, okay. This is this value expressing the distance moved by this body from t1 to t4, and it's always positive as well, okay. As we know, always distance okay, x is greater than or equal to displacement s, okay. As distance is always positive, displacement can be positive or negative, okay. We use here distance during calculating the average velocity, okay, but we use displacement while calculating average velocity vector, okay. We have an example. A particle moves in a straight line starting from rest distance 8 meter from a constant point on the straight line. If a acceleration equals 60 minus 4 meter per second square, find velocity and displacement, okay. Now we'll solve this problem by using indefinite integration. Then we have here acceleration equals 60 minus 4, and we have v equals integral a dt, okay. Then v equals integral 60 minus 4 dt. Then we have here 3t square minus 4t plus constant. As in indefinite integration, we have to add c and find it from the given data in the problem, okay. Then we have at v at t equals 0, okay. V also equals v node equals 0, okay. Then we can find c here equals 0 as well. Then v equals 3t square minus 4t, okay. This is required number 1, okay. To find the displacement, also we have x equals integral of v dt, okay. Then x equals integral 3t square minus 4t dt, okay. And x or displacement x or s, okay, equals t power 3, okay, minus 2t square, okay, plus c constant. As we use indefinite integrals, then we have to add this constant and find it. To find this constant at t equals 0, we have x equals x naught equals 8 centimeter from the origin point, or the point of the constant point on the straight line, okay. Then we have constant here equals 8, then 8 then x or displacement equals t power 3, okay, minus 2t square plus 8, and this is required to find, okay. Now we can solve this problem by using definite integration, okay. By using definite integration, we have here a equals 60 minus 4, okay. And by definite integration, we have v minus v node equals integral from t equals 0 to t, okay, a dt. a dt. Then we have v minus v node equals integral from 0 to t 6t minus 4 dt. Okay, then we have v equals v node plus this integration. Here we have 3t square minus 4t. Okay, and in this case we will not add this constant, okay, as constant here is expressed in this quantity v node. Okay, as while we are using a definite integration, we will not add constant as it's included in v node. Okay, there here v node here v node equals 0. Okay, from the given data, then we have v equals 3t square minus 4t. Okay, this is what we have obtained or found before. Okay, also we can find displacement by using a definite integration. We have x minus x naught or s minus s naught equals integral from zt 0 to t v dt. Then we have x equals x naught plus integral from 0 to t 3t square minus 4t dt. Okay, then we have x or displacement equals x naught here is 8 meter as given in the problem. Okay, plus by executing this definite integration, then we have here t power 3 minus 2t square. Okay, and of course we have to substitute from 0 to t, and will not add constant here as constant is expressed in this 8 meter given as x naught. Okay, then we have x equals here t power 3 minus 3t square plus 8. Okay, as we substitute by t first, then we'll subtract when t equals 0, then we'll find x or displacement equals x power 3 minus 3x square. Okay, plus 8 meter, and this is required to find. Now let's try to solve time. Okay, we have this problem. A car started moving from rest from a constant point on the line where v equals 3t square plus 2t meter per second. Find the acceleration of this motion and displacement when t equals 2 seconds. Okay, the answer is acceleration is 14 meter per second square, displacement equals 12 meter.